Welcome back to Mrs. Thompson's classroom. Today we're going to talk about complex numbers. We're going to perform operations with them and simplify expressions with them, including using their conjugates. So let's get started. First of all, we need to remember what a complex number is. So it's the set of all the real numbers plus all the imaginary numbers in any combination of the two. So a complex number can be written as a plus bi, where the a is the real part and the bi is the imaginary part. Okay, now we also want to remember what I stands for. I is the square root of -1. Okay, so that means I squared is equal to -1. Now, generally speaking, we can't take the square root of negative numbers because there isn't a number that when we square it, we get a negative number. And that's why these are referred to as imaginary, because we really sort of think of them as things that don't exist. But that's sort of a misnomer. These numbers do exist. They do actually happen in circumstances with some of our functions, in particular quadratic functions, sometimes have complex roots. And so we're just trying to distinguish them from the real numbers system. And so imaginary or complex are the terms that we use. Now this Venn diagram here shows how they're kind of broken up. So the whole box there is the set of complex numbers. If the b is 0, then the imaginary part goes away and we just get the real numbers. If the a part is 0, then the real part goes away and we get the imaginary numbers. If a and b are not 0, then we get this set in the middle that will look like a plus bi because neither of them are equal to 0. All right, so let's see what we can do with these. First of all, we want to simplify them. So we want to remember that when we're taking the square root of a negative number, so first of all, let's think about this as 5 times -1. So that would be like the square root of 5 times the square root of -1. And the square root of -1, this part right here, is equal to I. So our end result is the square root of 5 times I. Now, generally speaking, we're going to put the I in front because we don't want it to look like the I is underneath the radical. Okay, so with the square root of -36, again, we have 36 times -1. The square root of 36 is 6, and the square root of -1 is I. So we get 6I. Now, when we're multiplying them together, we can do the multiplication and then simplify, or you can simplify and then multiply. This is commutative. So, but we do want to make sure we keep track of the negatives as we work through it. So this whole expression would be like 2 times 18 times -1 times -1. We have two negative signs. Okay. All right. So 2 times 18 is the square root of 36, which is 6. The square root of -1 squared, well, that's like the square root of -1 times the square root of -1. So that's 6I squared, which is -6. Okay, so we want to just multiply those two negatives together and get a positive and say the answer is 6. But when we're underneath the square root, those two negatives do result in that I squared, and so we do end up with a negative result. So just be careful with that. Okay? Now, for two complex numbers to be equal, this would imply that the real parts are equal and the imaginary parts are equal. So in example 2 here, I'm going to take the real parts So let's rewrite this down here. So I'm going to take the real part and set them equal to each other. And that would give me an x equal to 5. Okay, and then I'm going to take the imaginary parts and set them equal to each other. Okay, so this would tell me that 3 would have to equal 2 minus y. So if I subtract 2 over, I get 1 equals negative y. So that means y equals negative 1. Okay. All right, now we can also combine complex numbers with addition, subtraction, multiplication. So when we're adding them and subtracting them, we really are just thinking about them as like terms. So I'm going to have the real part, and then I'm going to have the imaginary part. So I can regroup them. Addition is commutative and associative, so I can move them around and regroup them, and I end up with 6 plus 2i. When I'm subtracting, I'm doing the same thing, but I just want to be careful with that negative sign because this negative 2 is going to get distributed through here. So I end up with negative 4 plus 12i. Now I can group my real parts, so 3 minus 4, and I can group my imaginary parts, so negative 4i plus 12i, and I get negative 1 plus 8i. Okay. All right, we can also multiply them. So in this first example, example 5, we're going to FOIL, which we remember from algebra class, just means first, outside, inside, last. So my first would be 3 times negative 2. My outside would be 3 times 4i. The inside would be negative 2i times negative 2. And then the last will give me negative 2i times 4i. So I end up with negative 6 plus 12i plus 4i minus 8i squared. So negative 6 plus 16i minus 8. Then I squared is a negative 1. So we have negative 6 plus 16i plus 8. So the final answer is 2 plus 16i. Okay, in example 6, we're going to distribute this through. So I get 3 times the square root of negative 2 plus the square root of negative 2 times the square root of negative 2. So in here, this negative is going to pull out an I. And then the square root of negative 2 times the square root of negative 2 is just going to be negative 2. Okay. Now, to show why that works that way, let's think about it this way. That's the square root of 2 times I times the square root of 2 times I. So that's I squared times the square root of 2 squared. I squared is negative 1. And the square root of 2 squared is 2. So I get negative 2. Okay? All right, now we do want to write this in the standard notation would be to put the real part in front. Okay, in example 7, we're going to FOIL this out. When I square something, it means I'm multiplying it by itself. So let's FOIL. So my first is 2 times 2. The outside is 2 times the square root of negative 3. The inside is 2 times the square root of negative 3. And the last is the square root of negative 3 times the square root of negative 3. So I end up with 4 plus 4 square root of negative 3 plus, remember both of these negatives, that means I'm going to have I squared times the square root of 3 squared, just like we did up here. So I end up with 4 plus 4I minus 3, because the square root of 3 squared is just 3, and I squared is negative 1. So I end up with 1 plus 4I square root of 3 as my final answer. Okay, my last thing that we haven't done yet is to divide. So let's talk about division with these complex numbers. First of all, we need to know what a conjugate is. A complex conjugate is if we take z equal to a plus bi, its conjugate, which we denote with this little bar on top of it, is a minus bi. Now, why are these useful? Well, when we multiply a value times its conjugate, watch what happens when we FOIL this out. The first is a squared. The outside is a bi. The inside is a positive a bi. And the last is minus b squared I squared. So the outside and the inside go to 0. And I'm left with a squared minus b squared I squared. But I squared is a negative 1. So what I really have is a squared plus b squared. And we notice we end up with a real number. No more i's. No more imaginary part. So when we're trying to divide complex numbers, this I in the denominator, remember, is a square root. We don't like square roots in the bottom, so we want to rationalize. And so we're going to do that by multiplying by its conjugate. So 4 plus I. And then whatever I do to the denominator of a fraction, I have to do to the numerator so that this is like multiplying by 1. And I don't change the value of the fraction. Okay? So let's FOIL this out. In the numerator, I'm going to have 2 times 4 plus 2i plus 12i plus 3i squared. In the denominator, if I follow this example here, what I'll end up with is 4 squared plus 1 squared. Okay, if you want to FOIL it out, you'd get 4 times 4 plus 4i minus 4i minus I squared. So the outside and the inside go away, and I end up with 16 plus 1. Okay, so this simplifies to 8 plus 14i minus 3, because this I squared becomes a negative 1, all over 17. So I get 5 plus 14i over 17. Now, if we want to write this in a standard notation for complex numbers, I would split the real part and the I part up. Okay? All right, so we'll do a little more with complex numbers in the future. We'll be able to graph them, and we'll kind of relate them to some other things that we do later on in the year. But for now, this will give us a little idea so that when we talk in specifically when we're solving quadratics, which we'll do tomorrow, we'll be able to use our I's and our imaginary numbers correctly. So we'll see you next time.